Hello students, today we are going to study about the application of equilibrium constant. Okay, so when we are talking about equilibrium constant, okay, it is applicable only when the reactant and product has attained equilibrium. If it has not attained equilibrium, it is not applicable. Okay, equilibrium constant is not applicable. Okay, when we talk about this equilibrium constant, it does not depend upon the initial concentration of the reactant and the products. Okay, but yes, this equilibrium constant depends on temperature. It is directly proportional to the temperature. If temperature increases, equilibrium constant also increases. Okay, now this equilibrium constant also helps in the predicting of the extent of reaction. Means what? That yes, it predicts whether the reaction is being to be complete, or it is only half done, or it is in equilibrium position, or it is not proceeding. Okay, so if the value of Kc is greater than 10 to the power 3, it means the product will be formed in a larger form. Okay, and if a reactant is forming a product in a larger form, it means the reaction is being to be completed. Okay, it is on the level of its completion. Okay, now if Kc is less than 10 to the power minus 3, the reactant here will be more. Okay, here if the reactants are more, it means the reaction is not going on properly, isn't it? It is not proceeding. Okay, and here it will not have the habit of proceeding of the reaction. Okay, now if Kc has the value of 10 to the power 3 to 10 to the power minus 3, okay, the appreciable concentration of the reactants and products will be there. It means the reactant and products are in an equilibrium position. So now we will be studying predicting the direction of the reaction. Okay, so here we will be predicting what the direction of the reaction. Okay, suppose any reaction if you are taking in equilibrium, you represent it in this form, isn't it? But if a reaction is there, okay, we don't know what it is at equilibrium position or at the starting phase or at the end phase. Okay, what will be used? A simple arrow. So this is representing just a reaction. Okay, so in this reaction, okay, at any point if we see that yes, how the reaction is proceeding, okay, it is calculated by reaction coefficient. Okay, and how it is done? This is the product, this is the reactant. Okay, same procedure. Okay, the sum of the products to the power raised to its what? The stoichiometric coefficient, isn't it? In reactants also in the same manner. So how we will be predicting the direction of the reaction then? We all know Kc is equilibrium constant now, isn't it? This Qc is reaction coefficient. Okay, it means what? At any point we are seeing the reaction. Okay, so when the Qc is greater than Kc, okay, it means what? It is a reversible, the reaction is in reversible direction. Okay, when Qc is less than Kc, it means what? Now it has got what? Time to make the direction in what? The forward direction, to proceed the reaction in forward direction. Okay, if Qc is equal to Kc, it means it is at equilibrium, because here Kc is what? The equilibrium constant only. So from the equilibrium just we are seeing it, or just we are comparing it, the Qc, if Qc is greater than Kc, it is in the reversible direction. If Qc is less than Kc, it will move to the forward direction. And yes, if Qc is equal to Kc, it is in the equilibrium position. The reaction is in the equilibrium position. Now we will be studying calculating equilibrium concentration. So here we are going to calculate equilibrium concentration. Okay, in order to explain this topic, I have taken a numerical, a problem of Ncert 7.8. Okay, and here is the numerical. 13.8 gram of N2O4 was placed in a 1 liter reaction vessel of 400 Kelvin and allowed to attain the equilibrium. Okay, the reaction is given N2O4, equilibrium sign 2NO2. Here you can see both are in the gaseous form, so it is in a homogeneous equilibrium position. Total pressure is given, that is 9.15 bar, and you have to find what? Kp, Kc and the partial pressure at the equilibrium. Okay, so in the previous classes also I have said to you, whenever a numerical has been given to you, what you have to do, you have to see the particulars given in the numerical. Okay, so the particulars are what? Given mass is given, isn't it? That is 13.8 gram. Mass is given of what? N2O4. Volume has also been provided to you. Temperature also has been provided. Okay, so when we are seeing here, yes, the mass is given. Here we can take out the number of moles. How do we take out the number of moles? Given mass upon the molar mass. Molar mass we can calculate it from N2O4. Yes, given mass upon molar mass, you will be getting the number of moles. So we can understand here that yes, we can here use the ideal gas equation, that is PV is equal to nRT. Okay, so PV is equal to nRT. Okay, so here pressure is not given. Okay, but yes, volume is given, that is 1 liter into 1, that is equal to what? Given mass upon the molar mass of N2O4, what is the molar mass? 92. If you calculate it, you will get into what? R value, you all know 0.083, isn't it? And yes, temperature is also given, so you can write here 400 Kelvin. When you will be calculating it, you will be getting the pressure of N2O4, and that it will be coming 4.98 bar. Okay, so now this we have taken out the pressure, which is the initial pressure, okay, of this N2O4. Now we will be seeing in the equilibrium position. So in the equilibrium position N2O4, okay, equilibrium sign 2NO2, the reaction, okay, initially yes, the pressure was how much? 4.98 bar. Now what happens in the equilibrium? Okay, some amount of here now what has been formed? NO2. Okay, that we can write what? NO2 form will be how much? Initially it will be 0. Yes, reaction proceeds, come to the equilibrium position, and yes, we can take or assume it as what? X amount formed. Okay, and here as it is 2 moles, we will be writing 2x. Okay, now but yes, as the reaction has proceeded to the equilibrium position, and here we have taken the value x, that much portion will be subtracted over here in the left hand side. So what will happen? This 4.98 minus x it will become, isn't it? So now here you can see total pressure is given. So what is this total pressure? Total pressure is this plus this, isn't it? So here, and it will be becoming how much? 9.15. Okay, so now how we will be calculating x now? So x is equal to 9.15 minus what? 4.98, and you will be getting the value of this x, that is 4.17 bar. Okay, so once you got the value of this x, okay, so now we will be calculating the partial pressure at equilibrium of what? This N2O4 and NO2. So for N2O4 it will become how much? Okay, here initially it was 4.98, isn't it? So it will be becoming how much? 4.98 minus this x value, okay, that is 4.17, and you will be getting what? The value is 0.8 bar. Okay, now for NO2, here it is 2x, it is written 2x, so value of x you have got over here 4.17, so 2 into 4.17 it becomes 8.34, okay bar. Now here, now how do we calculate this? This formula I have given you earlier, Kp is equal to what? The product upon the reactant here raised to the what? Stoichiometric coefficient. So now here product is this NO2, so 8.34 square upon what was the reactant N2O4 and what was the value? 0.81. Okay, just calculate it. You will be getting how much? 85.87. Okay, here we are taking what? Pressure, so it will be, unit will be bar. Okay, now we also know that yes, what? Kp is equal to Kc Rt to the power what? The change in the number of moles. Okay, so now Kp value we have got how much? 85.87, isn't it? Kc value we don't know, we are calculating this Kc because Kp we have calculated. Now what is left? Kc is left. So how will you calculate Kc? You know, with this formula only. Okay, so Kp value is 85.87 is equal to Kc. Rt value you know how much? 0.083. Temperature it is given for 400. Yes, difference in number of moles. You can see here it is 2 NO2 and here it is only 1 N2O4. So 2 minus 1, it becomes 1. Okay, so now just calculate this. You will be getting the value of this equilibrium constant also. That is how much? 2.586. I can write 2.6. Now let us study the relationship between equilibrium constant, reaction coefficient and Gibbs free energy. Okay. Initially in the chapter of thermodynamics we have studied that yes, change in Gibbs energy is equal to change in Gibbs standard Gibbs energy, okay, and plus RT ln Q. Okay, RT represents the gas constant, temperature is by T, this is natural log of what? Q. Q, now you know it is what? Reaction coefficient. Okay, so at the equilibrium position what happens? This Gibbs free energy, change in Gibbs free energy is how much? Its value is 0, and if we all know that in equilibrium position this reaction coefficient is equal to equilibrium constant. So now we will be putting this value in this equation. So now here change in Gibbs energy 0. I have written 0 over here. Okay, that is equal to change in standard Gibbs free energy. Okay, plus RT ln K instead of Q. Now what has came? K, because reaction coefficient is equal to equilibrium constant at the position of equilibrium. Okay, so now here change in standard Gibbs free energy is equal to what now? Minus RT ln K. Okay, so now what we'll be doing? Just we'll be solving this. When we will be solving, okay, what will happen? It will become what? Minus change in Gibbs free energy upon what? RT. Okay, that is equal to natural log K. Okay, now we are removing this natural log. Okay, and we are using this word which represents like E over here. Okay, to the power, now it becomes whole, this one becomes in power, to the power minus change in standard Gibbs free energy upon RT, that is equal to what? K. Now till this much you have understood. Now if the change in standard Gibbs free energy is less than 0, okay, so now what will happen? If it is less than 0, it means it is negative, and when we multiply with negative into negative, it becomes what? Positive. So here what will happen? This equilibrium constant will become positive and it will be greater than 1. And if it is greater than 1, what happens? The reaction becomes a spontaneous reaction. Okay, and if it is a spontaneous reaction, it means the reaction is moving in the forward direction. Okay, now if change in Gibbs free energy is greater than 0, it means it is having a positive value. So that positive value into the negative value, okay, what we will be getting? Positive into negative, it comes negative now. So what happens here? Equilibrium constant is less than 1, and yes, if equilibrium constant is less than 1, the reaction is non-spontaneous. Okay, so if it is non-spontaneous, so what will happen? It will move to the forward direction only for a certain small degree of extent. Okay, so students, I hope you might have understood it. Good day, take care.